Morning, all.
Morning.
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 All right, let me organize windows here. Oh, to the left. All right, yeah. Does that work, Jeff? All right. I'll probably forget partway through, and you'll have to remind me to push it back again. All right, I'll wait just a minute for stragglers. I'm struggling to think of an interesting story to tell you from quarantine, but I don't have any. Maybe somebody else does.
Here's the story of how I did nothing for 2 weeks straight.
All right, except study for the second try exam.
This was before.
Oh, all right, all right.
Class before the semester started.
All right, yeah. Well, hopefully by fall, I assume most people in this class are probably freshmen or sophomores. So by fall, you'll return to kind of normal college experience. I always feel bad, especially for the freshmen. Like you're going to go to college and then you didn't.
Cheers to the freshmen who have had a rough 2 semesters.
Yeah, right. Ruined their senior year.
Yep, I was there.
Right. Senior year of high school spent sitting in a room. And then freshman year of college spent sitting in a room. So Gavin, do I know when the exam retake will be graded? Whenever the slowest of the 3 graders gets his act together and finishes, and the slowest of the 3 graders is me. So I don't know. I hope by I hope by the end of the weekend. Right? What's today? Thursday. Yeah. So hopefully by Sunday. I think the solutions are already up. So, you can kind of get a feel for how you did. Look at your solutions and the posted solutions, and you can kind of get a feel for how it went. In terms of points, we always just basically split the parts. If there's 2 parts, they're each worth 10. If there are 3 parts, it's 7, 7, 6, or 2 parts have 7, one part has 6 points. But all the problems are out of 20. Okay, let's see. Anything else administrative before we start?
If I'm in quarantine right now, do I have to come to class or can I leave?
If you're what?
If I'm in quarantine right now, do I have to come to class or can I leave?
What do you mean?
Just like if I were to be in quarantine right now or like next week, whenever, if someone is in quarantine, do they have to come to class on Zoom?
Well,
That's why we do it over Zoom.
I mean, we're over Zoom, so
yeah, but still, it's just a class.
That's true. I mean, I don't know how good Zoom is at blocking the virus.
It's a computer virus as well.
Yeah, I mean, there's a reason I always have zero attendance policies for classes that I teach. I don't think people should do things to make people come to class. If class isn't useful, and you want to study on your own, it's totally fine. Oh yeah, if you're off by 10 to the minus 3, a lot of people were off by 10 factors of 10 to the minus 3 or something in like problem 4. You wrote joules instead of millijoules. It's not big. It's not that big a deal. It's little. It's the same thing. It's like if somebody goes through in problem 1 and they get all the vectors right and they do everything correctly, and then they drop a factor of 2 when simplifying, that's worth like maybe 1 point out of 20. So yeah, this came up. This came up. I was talking to somebody, I can't remember who, about the problem with, with the cube, and you have, so solutions are up, so you can look at them. But this one, what's the flux, the total flux through all the walls of this thing? This is not a bad one to, we're not going to go over the test, but you can, if you want help on it, you can come to office hours after you read the solutions and see what you need help with. So if these sides have a length of L, then you know that E dot dA is equal to Q enclosed over epsilon naught. That is Gauss's law. And that is a synonym for the flux. So Gauss's law tells you the flux through the walls of any enclosure is just equal to the charge inside it divided by a constant. And so I don't want to get into tons of things about like what points are different things worth, but so in this answer, this thing had a charge density of lambda. And so so phi E is just Q enclosed over epsilon naught, and charge enclosed is just the linear charge density lambda times L. So it's lambda L over epsilon naught. And that's the whole problem. Which is not to say, right? So it's very short, which is not to say it's trivially easy, because you gotta, it's conceptually subtle to understand that this is the flux, and that the flux that the only thing you really need to get the flux through the walls of an object is the charge inside it. To make that connection is not simple. So just because this is short doesn't mean it's a trivial problem. But in terms of, this always comes up with things like partial credit on problems. So if you go through this, whatever this problem was with the charges, and you find the E field at this point, and you go through and you have all these vectors and everything, and then at the end, but somewhere in here you screwed up and you had a factor of 2 or 6 or something that you added wrong. It doesn't matter. It's basically still right, because it's clear you know how to add vectors, and you know what you're doing, and you just dropped a factor of 2 or 6 or something, and that doesn't matter. Or you squared something, you forgot to square something, and that's not a big deal. And so it's still worth almost all the credit, even if your answer is wrong. But honestly, like in this problem, if there are things like, well, there's a 6 here because there are 6 faces, that, the problem is wrong. That's not how to do the problem. So even though the answer looks similar to the answer, this is not close to correct. But this, with a factor of 6 off of it, is really still close to correct if all the vectors are there. So that's my only point. When you're reading through and looking, at partial credit, if you're trying to estimate how you did, you have to be honest with yourself. Did you really just lose a sign somewhere in here and adding and subtracting, or was there a conceptual problem in the solution? Yeah. So, Christina, I'm not sure. I don't know. Let me look through, and I don't know whose is whose. We grade them blindly, so we don't see names when we grade papers. Okay. So let's see. Yeah. So we're switching gears a little bit. So we're starting in, I forget the chapter number in the open source. It's 29 in Survey. In the open source, it is 11. So we're starting with magnetic fields. And there are a couple things. This chapter is not quite as hard as the next one, but it's a step harder than the previous chapter on adding resistors and resistor networks and Kirchhoff's laws. So what I can tell you that is the basic, let's do a little comparison between E fields and B fields. right? So you know that E fields are produced by charges. And then also, you know about E fields, you know it's a vector field. You also know that E produces a force on other charges. Um, and yeah, okay. So the path that you take here is given charges, you find E fields. I guess that's sort of just a synonym for this, right? So the path we always take, we say, okay, well, just think what you did on the last exam, on the second try or the first exam, whatever. You have some plus Q, I don't know, plus Q plus 2Q, and you can say, well, what's the electric field there? And you know how to do that. You know, each of these charges produces an electric field at this point, and so you'd have a vector that goes like this, and one that goes like this, and one that goes like this, and then you'd add them, and you'd get a total E field at this point in space. And you could also find the E field here, or here, or here. And so it's a vector field. Every point in space has a vector associated with it. And you also know that the E field produces forces on other charges, and the force that it produces is Q times the electric field. So if you know the electric field here, and I say, okay, you put some charge capital Q here, you know the force on this charge from these is going to be capital Q times the electric field where this charge is sitting. Okay. So how does that compare with magnetic fields? So magnetic fields, they are produced by moving charges, not by just plain charges sitting still. B fields are produced by moving charges. It is also a vector field. So here we have a vector field E. Every point in space has some vector E associated with it. We use B for magnetic fields. If you're looking at things online, sometimes you'll see H, and it's slightly different. So just be careful. So we're not going to talk about H fields. But so for us, so vector field B. So charges produce vector field electric fields. Moving charges produce magnetic fields. And then B produces or imparts a force on other moving charges. So electric field charges produce electric fields, and electric fields cause forces on other electric charges. Moving charges produce B fields, and B fields produce a force on other moving charges, not just charges sitting still. So if you have a magnetic field and you have a charge sitting still in it, that charge won't feel any force. And we'll talk about this is what we're going to spend a lot of time on this whole chapter. And so you say, well, here, the force on a charge in an electric field is just Q times E. So the force on a charge is always in the direction of the electric field. It's just scaled up by a size of Q, right? E newtons per coulomb times Q coulombs gives you a certain number of newtons. The force on a charge, on a moving charge from a magnetic field is going to be Q. And don't worry that you haven't seen this or might not know what this is. We're going to spend a lot of time on this equation. So the force is Q times V vector, the velocity vector of the charge, crossed with the B field. And so you do the same thing. So given moving charges, you can find B fields. Okay, so you would think the natural order of things the first thing we would do is I would say, okay, we're going to have some charges moving here. You'd think, all right, so we're going to have some moving charges. Maybe they're moving this way, and let's find the B field at that spot. And in practice, what a bunch of moving charges is really a current. So you would think the first thing, logically, the thing to do is to say, all right, you have some wire carrying current I, that's moving charges. What's the magnetic field here? Just like we did with electric fields. You put a bunch of charges someplace, and you say, okay, what's the electric field there? So logically, the first thing we would do is learn to find the magnetic field from currents. And then you'd say, okay, now I'm going to put a moving charge at this spot that's in a B field. Let's find the force on it. That would be the logical order to go. First, you find out how to make B fields, and then you talk about the force that those B fields apply to other objects. But we don't do it in that order. We're going to follow the order of your textbook, which is in this first chapter, we just say from God knows where, just somehow there is a particle of charge Q, let's say moving with velocity V, and somewhere from out of the blue, there's a magnetic field. We're not even going to talk about how this magnetic field was produced. We're just going to say there's a magnetic field that goes this way. And you might wonder, it's kind of odd. It seems backwards. The reason it's done that way is just for calculations. It's a little harder. Finding B fields from current is harder than finding the force on a charged particle in a B field, just in terms of how advanced the calculations are. And so we do it in this logically reversed order. In this chapter, we're going to just assume B fields come from somewhere without worrying about where, and find the force on charges in B fields. Okay. Just checking the chat. Okay. So this is an entire chapter about this equation. This is basically the whole chapter. All right, so let's take a minute to look at this. All right, questions so far? All right, so let's look at this equation. This is known as the Lorentz force equation. And it's an experimentally determined function. It is found, right? We don't derive it from anything. So the force on a charged particle is Q times V vector cross B vector. Okay. So what does that mean? So if I take, let's suppose somewhere, again, don't worry about from where, there is a magnetic field B that points in this direction. And B, as we'll learn later, these have units of Tesla, named after Nikola Tesla, not the car. So let's say we have a magnetic field of strength B pointing in this direction. And then let's say I have a particle of charge Q just sitting here. If it's just sitting there, the force on it would be nothing. But let's now suppose that this thing moves in this direction with some velocity V. Okay. All right, so V represents the velocity of the particle. Q is the charge on the particle. B is the vector magnetic field. So V is the velocity vector. And so this thing together gives you the force on that. Okay. One thing to notice is, so the force is proportional to Q, V, and B. So there's no vectors over those. I mean, the speed is proportional to the speed, it's proportional to the magnitude of the magnetic field, and it's proportional to the charge. Meaning, obviously, if you look at this thing, there's some force on this, and if I were to double the velocity, I'll double the force, or the charge, or double the magnetic field, I'll double the force. So it goes linearly with all three of those. But because it's a cross product, but it also depends on direction. Okay, so before we go any further, I want to do a quick review of dot products and cross products. And this is one of those places where you really must slow down and go, even though you basically know, I know you all know what dot product and cross product is, but there's a tendency to think, oh, A dot B is AB cos theta, A cross B is AB sine theta. All done. And that's not good, because as you know now from doing some physics, you have to be very precise about your understanding of these sort of seemingly simple quantities that you've known for years. So A vector dot B vector is equal to the magnitude of A times the magnitude of B times cosine of the angle between them. So if I have a vector A and a vector B, A vector dot B vector is this. Right? Okay, good enough. The first thing to notice is this is a number, right? Because that is a number. It's the length of A. That's the length of this vector. Cos theta is a number, so you just have a product. It is not the case that A cross B, right, is not equal to AB sine theta. It can't be equal to AB sine theta because this is a vector and this is a number. Cross products are vectors. So what is really true is that A vector cross B vector magnitude, right? Because this object, A vector cross B vector, is itself a vector. The output is a vector. And so I can do this, and that means take the magnitude of that vector. That is equal to AB sine theta. Right? And you think, yeah, whatever, it's AB sine theta. But it's not, and we have to worry about the direction of things. Okay, so A cross B has a magnitude of AB sine theta, and the direction of A vector cross B vector. You can do this is from the right-hand rule, which we're going to review, or just carrying out cross products, or just doing the algebra. And I'll show you what I mean in a second. Okay. So let's look. So in our little review of cross products here, let's just look at so X is sort of coming out of the page toward you. Y is going this way. Z is going that way. All right. So let's do a couple of cross products and use the right-hand rule to do them. So I want you to do X hat cross Y hat. All right. Well, X hat, we know the magnitude of this. So the magnitude of X hat cross Y hat, that's going to be equal to the magnitude of this, which is 1, times the magnitude of that, which is 1, times sine of the angle between them. And sine of the angle between X hat, which is a vector going the X direction of length 1, and Y hat, which is a vector of length 1 going in the Y direction. The angle between them is pi over 2. And so we have sine pi over 2, which is also 1. And so the magnitude of X hat cross Y hat is 1. The direction of X hat cross Y hat, you have to get from the right-hand rule. So the right-hand rule, and this, many people, they just either they know it or they get it quickly, and some people just struggle with this. So if I have a vector like this, A, and a vector like this, B, to get the direction of A vector cross B vector, I take my fingers and I run them I start at A and I move them toward B and of my right hand. And then I see which direction my thumb points in while I'm driving the tips of my fingers from A toward B. And my thumb points out. So the direction of the vector A cross B is out of the page. So here, if you do that same thing, oh, I'm sorry, one other thing. So find the direction of, if this is A vector and this is B vector, find the direction of A cross B. So just take a second and think about that. So there's A vector, from there to there, and B vector is from here to here. Find the direction of A cross B using the right hand. A vector cross B vector using the right hand rule. Well, it's the same actually, because vectors do not have locations. Vectors have magnitudes and positions. So when you have two vectors in different places and you want to do the cross product, just pick one of them up and move this over to here. So this thing is the same problem as that one. So A cross B is still out of the page. A couple of things to note, because right-hand rule can be tricky when you get vectors going in all different directions. The first thing to note is that A vector cross B vector for any two vectors is perpendicular to A vector and perpendicular to, I guess I don't need the 2 in there, B vector. All right, think about this. This is an important statement. A cross B, this itself is a vector. The result, this thing, when you're done crossing it, is a vector. And that vector that this thing is perpendicular to both of the originals. So that means, in this case, before you do any work, and this is an important thing to do for once we get going, and we're going to use cross products a lot throughout the rest of the semester. And so the first thing to do is, before I do anything else, when I see A vector cross B vector, the first thing I do is I say, look, the direction of A cross B, it has to be perpendicular to A and it has to be perpendicular to B. There are only two directions that are perpendicular to both of these vectors. Out of the page and into the page. That's it. No other directions are perpendicular to both of these. And so you are only using the right-hand rule to choose between two options. There will always be only two options that are perpendicular to both of your input vectors. And the only thing you're using the right-hand rule for is to choose between those two. So my only options in this case are out and in. And I'm just using the right-hand rule, going from A to B, to choose between those two. And it tells me that it's out. So here, we're looking for x hat cross y hat. We know that its magnitude is 1. So it is a vector of length 1. And now we need to know its direction. There are only two directions that are perpendicular both to x hat and to y. X hat, sorry, comes out of the page. Y hat goes this way. And so this is x hat. This is y hat. There are only two directions that are perpendicular both to this and that. One of them is this, and the other one is this. So z hat and minus z hat are the only directions that are perpendicular to both x hat and y hat. So you are only using the right-hand rule to choose between them. And so I'll use the right-hand rule. So x hat goes this way, y hat goes across the page. So I drive my fingers from x hat toward y hat of my right hand, and then my thumb points that way. So the direction of x hat cross y hat is z hat. So we have a vector of length 1 in the z direction. So what we know is x hat cross y hat is equal to z hat. Okay. And notice, so questions so far? Yeah, do an example and it's in instead of out. Yeah. So take, why don't you take a second? Why don't you figure out what y hat cross x hat is? So Patrick and everyone, just take a second on your own and figure out y hat cross x hat. It's a vector. So do this cross product. So just take a minute and work it out. Do the right-hand rule. Okay, so we know it's going to be the magnitude of y hat cross x hat is going to be 1, which is the magnitude of that, times 1 magnitude of that, times sine of the angle between them, and the angle between them is pi over 2, so it'll be sine pi over 2, which is 1. So the magnitude of y hat cross x hat is 1. The direction of y hat cross x hat. So now I need to do a right-hand rule between y hat, which points that way, and x hat, which points that way. Again, there are only two directions that are perpendicular to both of the input vectors, z hat and minus z hat. So I'm only using the right-hand rule to choose between them. And so I drive my fingers from y hat toward x hat, which is this way. Sorry, I got to move my, I'm going to do it up here. Right, so I've got, sorry. Yeah, y hat goes, now I have to twist it because now it's coming out of the page and now I'm facing you this way. So we have x hat is toward me, y hat is this way, z hat is up. So x hat cross y hat, x hat is toward me, x hat cross y hat was up. Y hat cross x hat is down. So it's minus z hat. So the direction of y hat cross x hat is minus z hat. So what we know from all of that is that, y hat cross x hat is minus z hat. A vector of length 1 in the minus z hat direction is minus z hat. So notice that if you reverse the order of the cross product in this case, you flip the sign of its direction. You flip its direction, right? Okay, so can you think about questions for a second? And Patrick, does that answer your question? Okay, sometimes it's pretty easy to do. Like if you have some vector, A, like if this is vector, well, let's just do these, right? So let's say we have a vector A and B, and you say, what's the cross product? Well, you say, I don't know. You got to tell me what the angle between them is. Well, let's suppose it's theta. Okay, then A vector cross B vector would equal magnitude of A times magnitude of B times sine of theta, but that's not the right answer yet because it doesn't have a direction, and this has a direction. So this would be A, the magnitude of A vector, times B, which is the magnitude of B vector, times sine of the angle between them, and the direction would be out of the page. So I would just write that out hat. Right, a vector of length 1 that comes out of the page. B hat cross A hat would be this same magnitude and would be into the page. All right. But sometimes so questions on this? Do you always go the shortest way possible? Yes. There's another, for anybody who's ever used a screwdriver, there's another way to think about directions. It's called a right-handed coordinate system. And, if you go to Home Depot and you buy some wood screws, if you somewhere on it, it's assumed they're right-hand threaded screws, meaning if you twist the screw this way, it will go into the page, right? If I put a screw here and I twist it like this, right? So if you take your right hand and you twist like this, clockwise viewed from above, then it will go into the page. If you twist this way, it will come out. So it is a right-handed thing. So you're twisting from here to here. Right?
Have y'all ever dealt with a left-handed screw? They're the worst.
Yeah, and in fact, if you're into cycling at all,
Yeah.
cranks one
It was with
side
my
of
bike.
bike cranks are left-hand threaded. That's so that when you pedal, both sides tend to get tightened as you pedal. Not otherwise, if you had right-handed screws on both right-hand threaded on both sides, then gradually one side would tend to work itself loose. So it's just another way to think about it. This corresponds to inward, and this corresponds to outward.
Can you please show one more time what you're doing with your hand when you do the right hand rule? One more time.
Yeah. So if you're going if I'm trying to cross, I don't know how visible this is, right? Blue cross black. I need to run my fingers. Two ways to think about it. One, if you want to think about it in terms of wood screws, imagine poking a screw here and then twisting from blue toward black. What direction would the screw go? It would go this way. Actually, I should do it like this because you're looking. Let me get this so it's more visible, right? So from blue to black, my right hand goes like this, and so my thumb points that way. Right? Cross product of the black cross blue would be that way. Right? Is that okay, Evan?
Yeah, that's yeah, that's good. Thank you.
Yeah. So Joseph, yes, we're going to talk about that in a minute. So X hat cross Y hat is Z hat, but you should on your own go through and do the others. Not right now. We don't have time for, you need to do Y hat cross Z hat cross X hat. You should be able to do all the combinations in either order. And once you do a couple of them, they're really not hard. And the first thing you notice is that it's always going to be the missing one. So Y hat cross Z hat, the direction of that, it's got to either be X hat or minus X hat, right? It can't, because it's got to be perpendicular to both of these. And this has got to either be plus Y hat or minus Y hat, because it has to be perpendicular to both. So I'll do these quickly for you. Y hat cross Z hat, Y would be out of the page. So that would be X hat. Z hat cross X hat. So Z, then moving toward X, which comes out of the page, is that way, which is Y hat. So there's a little, I hate mnemonics in general. This one, it's handy to help you remember things. But really, trust me, you should only use this after you can really do them all on your own. So this just a way to remind you, X hat cross Y hat is Z hat, Y hat cross Z hat is X hat, Z hat cross X hat is Y hat. And if you go the other way, it's negative. So Z hat cross Y hat is minus X hat. But you should use this little mnemonic to check your answers on doing all the cross products with the right hand rule. Okay, so this is fine for simple cases like, we got both the vectors on this plane and I know the opening angle between them. But that's not always how you have vectors. You might have a vector you might have two vectors like, let's say you have some vector A is A sub X, X hat, plus A sub Y, Y hat. And you have another vector B, which has some X component. B, so it's a mix of this much X hat and this much Y hat, B sub Y, Y hat. And now what's A vector cross B vector? Well, I guess it's magnitude of A, which is square root of A squared plus AX squared plus AY squared, times magnitude of B, which is square root of BX squared plus BY squared, times the sine of the angle between them. But I don't know what the sine of the angle between them is. Now you can go through and you can, write this as components and write this in components and figure out using some trig, what the opening angle between them is, and you'll get the right answer. But you can also do it algebraically, as Joe pointed out a minute ago, right? So you could write this as a sub x, x hat, plus a sub y, y hat, crossed with b sub x, x hat, plus b sub y, y hat. Okay, and now you have to push ahead, and you're going to have 4 terms. You'll have this cross that, plus this cross that, plus that cross that, plus that cross that. Right? So this thing will be equal to a sub x times b sub x, remember those are both numbers, times x hat cross x hat, plus a sub x b sub y times x hat cross y hat, plus a sub y b sub x times y hat cross x hat, plus a sub y b sub y times y hat cross y hat. All right, so good. We've got these 4 terms. Why don't you take a second and finish this? Try to finish this, right? Figure out what that is. That, and that, right? Each of these 4 things is a vector. So you're going to have this times some vector plus this times some vector and so on. Right? So in principle, you have 4 terms. So why don't you try to work that out? Even if you have no idea what you're doing, write something down. I don't know why human brains work that way, but there have been, I've seen at least 3 studies that show that if you try to write an answer down for something, even if you have no clue what you're doing, and even if what you write down is nonsense, you'll remember the actual answer better, which is weird. I don't know how that can be. But I mean, as long as you're making an effort, obviously, if you just, make marks on a page. So make an effort to figure something out for that if you don't know what you're doing.
I feel like it has something to do with not wanting to feel like an idiot.
Well, no, I don't know, because in this case, right, nobody can even see your paper. Nobody knows what you're writing down.
But you know that you were wrong.
There you go. But right. So just try to write some. They think it has something to do with if you form an opinion and then see an answer that's different than your opinion, you kind of somehow it sticks better. But you need to form an opinion first. Is different than just hearing what the correct answer is. So you should wind up with 4 terms. I'll give you a hint. Some of them may be 0. Okay, I'm just speaking gibberish now. All right, well, I'll stop. Okay, so here, this term, we're going to have this number times x hat cross x hat, but this is 0, right? Because the magnitude of this is 1 times sine of the angle between x hat and x hat. But x hat and x hat point the same way, so this sine is 0. So that's 0. Similarly, this is 0. X hat cross y hat is equal to z hat. And y hat cross x hat is minus z hat. So these 4 terms together are a sub x, b sub y times z hat. I'll just do it that way. Minus a sub y, b sub x times z hat. Or we could just simplify that and write a sub x, b sub y minus a sub y, b sub x times z hat. Okay. All right, so think about questions so far. Okay. So some cases,
Wait,
the
I do have a question.
Yep, go ahead.
So how do we know that x hat equals 1?
We don't know that. So yeah, x hat is not 1 actually. X hat is a vector, and so it has a length and it has a direction.
Okay.
And its length is 1. So unit vectors, that's why they call them unit vectors, have length of 1 and then some direction. So what we really did here is we said this is 1 times sine of 0.
Okay.
Right? And I guess to be a little more particular, to answer your question more properly, right? We know these have length of 1 because that's how we represent a vector by how much times a vector of length 1 in some direction plus how many of a vector of length 1 in another direction. So if you wanted to make unit vectors be, your basis vectors be twice as long, then these factors would have to be cut in half. What happened to the sine theta? Right. So Asa, the sine theta, and then Michael, I'll get back to your question. Sine theta is here, right? Let's say this one, y hat cross x hat is equal to 1, magnitude of that, times the magnitude of x hat, which is also 1, times sine of the angle between them. The angle between y hat and x hat is pi over 2. And so sine of this becomes sine of pi over 2, which is 1. Right? And then you think, well, but wait a minute, somewhere in there, somehow in this answer, there's no sine anyplace lingering. It's the impact of the opening angle between these, what would be the sine of them, is buried in how big this thing actually is. Right? So you could instead find, maybe A points this way and B points that way. So there's A vector and here's B vector. And this has some x component, right? There's some A sub x and A sub y, and there's some B sub x and B sub y, and there's some opening angle between them. And so if you found this opening angle, just call it phi. If you broke these into components and did the trig and found this angle phi, when you found the magnitude of this length times sine of that, you would get this. So the effect of what the angle is between A vector and B vector is in here, or it's in sine of this. So when you actually did the trigonometry, you'd wind up finding things that looked like this. So should we always refer back to that circle of y hat, z hat, x hat? Jeffrey, yes. And so, yes, you can refer to it as a quick cheat to make sure you don't make a mistake in crossing. But it's very important to make sure you can do the right-hand rule properly, that you also try. There's only like 6 combinations anyway. Try them on your own to make sure that you actually see why, for example, x hat cross z hat is minus y hat. Right? X comes out, z goes up, and so x hat cross z hat would point this way, which is minus y hat. So you gotta make sure you understand why this works. And so, so Michael, are you clear now on why x hat cross x hat is 0? Other people are answering your questions. Right? They point. Sorry, go ahead.
I got it.
Okay. All right. Other questions? Okay. So that's great for vectors in 2 dimensions. Which side is negative? Let's say I don't understand that question. Can you unmute?
So like how did you know it was negative y hat and not a positive y? Because you said for this example, right?
Oh, for x hat, y is x hat cross z hat and negative y hat?
Yeah.
Yeah. So this has nothing to do with that, right? The coordinate system is x hat cross z hat. X hat cross z hat is minus y hat, because if x hat's coming out of the page, and z hat, z hat goes that way, y hat goes that way, and x hat comes out of the page, then x hat crossed with z hat, I'm driving my fingers from x towards positive z direction, is this way, which is the minus.
Oh, okay, I see.
And then actually, but I'm glad you asked that, because I forgot to say something, right? You say, well, maybe you draw this coordinate system differently. Maybe you make y go that way. And you could, but if you look in your book and everywhere else, you will always see the coordinate systems drawn such that they are right-handed, such that this works. And in fact, if you look carefully, when, in any math or physics class, when anyone draws a coordinate system, they'll always say, okay, we got x and we have y going like this. If you pay attention for a second, you'll notice there's a little pause before they draw the third coordinate, the third direction. And what the person is doing in their head is they're making sure that they draw a right-handed coordinate system, because it's convention. We could reverse everything and do left-handed systems, but we don't. And so if I drew this and we were doing a three-dimensional problem, and I said, okay, x is that way, y is that way, and I'm pausing for a second because I know I need x hat cross y hat to be z hat. And so I'd say, oh, okay, and z comes out of the page. Okay. Yes, so the physics gods can choose to be evil with a non-right-handed system, but for the sake of people's minds, let's not. When would y be up in a 3D coordinate system? So it just depends on what angle you're looking at things from, right? I mean, if you're standing here looking this way, x is in the up. So right, up and down are just, direction relative to what you're looking. And for those of us who are left-handed, it's always a struggle to live in a right-handed world, but that's how it is. Okay. All right. So what if you had, so any other questions? Everyone all right? So this is great for two vectors lying in a plane, but it could get worse than that. You could have, let's say you have, x, y, z like this. And in fact, if you look at this system is the same as that one. It's just you're looking from the side. So what would you do, though, instead, if you had one vector not on the plane, not on the page, pointing this way, and another vector pointing in some other random direction? Now you have the three components for this, an x, y, and a z, three components for this, and then now what are you going to do? Well, I guess really what you'd have to do, right? Because here, in this case, we've really made two vectors where we had z coming out of the page and so the z component was 0. So it was really plus 0 z hat plus 0 z hat. And so we didn't have to worry about that. But in general, you could have b vector is b sub x, x hat, plus b sub y, y hat, plus b sub z, z hat. And then you're like, you could do the same thing you did here. You just have 3 terms here, 3 terms there, and then you'd have 9 cross products to do. And when you did that, 3 of those 9 would drop out anytime you had, right? So if we were crossing this with this, you'd have that cross that, plus this cross that, plus this cross that, and then 4, 5, 6, 7, 8, 9 cross products to do. But this term, z hat cross z hat, 0, that cross that, 0, and that cross that is 0. So you'd have 6 of the 9 terms surviving. And you'd have to go through each one. You'd have to say, all right, x hat cross y hat is a z hat. And you'd have to do the arithmetic just like you did here. And there's nothing wrong with doing that. Eric, I'll get to your question in a second. But there's a shorthand that'll help you work this out. right? If you take the determinant of this matrix, you'll wind up doing the same thing as you would get from all of that messing around. So you'll get x hat times ay bz minus az by minus y hat times ax bz minus az bx plus z hat times ax by minus ay bx. Right. So if you just do the determinant of this, that'll give you the same thing as if working those 9 terms out like this, except it's less error prone to do this because it helps you keep all your terms organized. Okay. Finally, something familiar. Joseph, stop encouraging him. Couldn't you move your coordinate system to match the vectors? Yeah. All right, everyone, wait, stop chatting. I don't want to lose Eric's question, right? Couldn't you move exactly right. You could. If you had these 2 vectors and you didn't want to do it in 3D, you could just rotate the coordinate system so that they lay flat on one of the planes. You could do that, and then your cross product would be easy. It'd be easier. It'd be like this one. But now really you're just shifting the work because you're going to have to do a rotation to transform these 2 vectors into a coordinate system in which your basis vectors, in which they are on the plane of 2 of the basis vectors. So it wouldn't be easier. It would just be different work. And usually this is easier to do than to transform the vectors. All right. Yeah, 3 blue, 1 brown is outstanding for pretty much everything. I don't think I've ever, if you don't know what they're talking about, there's a set of online videos called 3 blue, 1 brown on various mathematical and physical things, concepts. And they are, I don't know, maybe second only to Richard Feynman. They're very, very good. Because they don't teach you just to memorize formulas. They teach you why things are true. And especially if you're a very visual person, they're really visual videos. Okay. I mean, some of them, they're not always easy, right? Because they're not teaching you, it's not like some Khan Academy or some other videos where they just teach you how to do stuff. He attempts to teach you why things are the way they are. And so they're not always easy. Okay, good. I was just checking chat for anything. Watch the video he sent. It's actually amazing. Okay. Yeah, watch the video. Don't watch the video now, though. Okay, so let's get back to, now we sort of have recalled what cross products are. And let's figure out how this relates back to magnetic fields and the Lorentz force. So what you know is that the force on a charged particle of charge Q, so we have a particle of charge Q moving with velocity V in some magnetic field, B points that way. We know the force on this charged particle, and this B field, covers this whole range. The force is going to be Q times V vector cross B vector. All right, so we can do, let's just do a simple example of this thing. So, well, before we do that, one way we could make the force on this thing be 0 is we could have this, if the charge were 0, then obviously the force on it would be nothing. Or we could make it move if the velocity of this particle were this way, the force on it would be nothing, because V vector cross B vector would be 0 because they point in the same direction. And what in this drawing, what's the direction of the force? Let's say this angle, actually, let me do something here. Let's say this angle is theta, and let's say this angle is phi. So the B field is down from horizontal. So these are both on the surface of the page. V is going up by theta. B is going down by an amount phi. So find QV cross B. Okay, so what would that be? And so write the direction too. Okay, so Q V vector cross B vector will be equal to Q times the magnitude of V vector, which is V, times the magnitude of B vector, which is B. So the charge times the speed times the magnitude of the B field times sine of the angle between them, which will be sine of theta plus phi. The angle between them is theta plus phi. Okay? Okay. Everyone okay on that? Okay. Let's see. I don't want to spend a ton of time on this example because I think it's a little too easy, but I want you to have to spend a ton of class time, but I want you to have the answer for it so you can work it out on your own. Let's just say you had let's take a B field of 2 Tesla, just to do one once in a while to actually have numbers in a problem. So a B field of 2 Tesla at minus 45 degrees. So meaning this angle is 45 degrees. And then let's say there's a something with a charge plus E. So let's say a positron or a proton moving this way with an angle of 30 degrees. Q equals plus E. And let's say the velocity is c over 2, half the speed of light. All right, find the force on this. And actually, before you do that, I made a huge mistake in this problem. What mistake did I make? No direction, exactly. Right? This cannot be equal to that because this is a force and this is a number. Right? So what's the direction? I need V vector cross B vector. What way is it?
Minus Z.
Yeah. Well, yeah, assuming Z, we didn't really call what's X or Y, but yeah, it's into the page because V goes this way, B goes that way, and so V cross B is into the page. And since I didn't define X or Y or Z, I will call that in hat. Or I could say it's negative this out hat. So in hat means a vector of length 1 going into the page. All right. Okay. All right. So find the force on this. Well, the first one, there's 2 ways to do this. I want you to do it both with components, and I'm mostly just going to give you the answer to this so you can make sure you get it on your own. Right. So force is Q V vector cross B vector. And so just basically it's the same thing we just had here. So this will be Q is 1.6 times 10 to the minus 19th coulombs, right? If it's plus E, charge on a positron or proton. V is 1.5 times 10 to the 8th meters per second, because C is 3 10 to the 8th meters per second. So we have Q times V times B. B is 2 Tesla. QVB, and now I need times sine of the angle between them, which is sine of 75 degrees, and the direction of this is into the page. Right, so you can work that out. If you plug those numbers in, you should get 4.66 times 10 to the minus 11 newtons in hat. Okay, that's really easy to do it that way. I wanted you to have this problem because I also think it's good as practice with vectors, especially those of you who have trouble with that. I want you to redo this problem, except I want you to do it properly with components and cross sections. Yeah, so Gregory, Teslas are just the units, and we'll talk about it more when we get into how B fields are measured. But it's a measure of strength for a magnetic field. And when 75 came from the angle between, this is 30 degrees up from horizontal, and B is 45 degrees down from horizontal. And so the opening angle is 30 plus 45. Everyone okay? Okay. So what I want you to do, work this out later on your own. I want you to put V, call this X, call this direction Y, write write V in components and write B in components, and then do the cross product in components, right? So you should wind up with V vector is 1.5 times 10 to the 8th meters per second. That's the magnitude of V, but I have to now break it into components. So it'll be cos 30 x hat plus sine 30 y hat. So I need this multiplied by a vector of length 1 that points in that direction. So that will be square root of 3 over 2 plus 1/2 y hat. So square root of 3 over 2 x hat plus 1/2 y hat. So that's a vector of length 1 that points that way. And B vector is going to be 2 Tesla times, that's the size of B vector, and I need it to be a vector that points this way, 45 degrees down. And so that will be plus 1 over root 2 x hat minus 1 over root 2 y hat. So now you can cross these things, right? You'll get this cross, this times that with a z hat, and this times that with a minus z hat, because you have to do V cross B. So when you cross these things out and multiply by Q, you should get minus 4.66 10 to the minus 11 newtons z hat. So in the negative z hat direction. Right, so you do the cross product on your own after class. Okay, so think about questions so far. Yep. Yeah, Ender, yes. Break it into components and then find the determinant. I mean, in this case, you don't really need to write out a full matrix, because you can just do, right, there's only 4 terms to do, so it's easier. But if you want, you could write it in a matrix, and you'd get, you'd have x hat, y hat, z hat, and then the z component of this vector is 0, and the z component of that vector is 0. So when you do the determinant, you'll only get this times that minus that times that, because your other ones will go to 0, right? But yeah, you can write it this way if you want to and do the determinant. Just make sure you put z components 0 for each vector, because they are, right? No z component in V or B. Okay. All right. So if you have let's say you have a charged particle moving here with some velocity v, and it's in some B field, I don't know, that points this way. And it's also in an E field that points this way. And you think, oh my God, this is getting out of hand. But right, it's not really any harder. Nothing much changes. Right? So the force on this particle of charge Q moving with velocity v this way is going to be pretty much what you'd guess at this point. Right? So the force on Q is going to be, well, just because there's a force on it from a magnetic field doesn't change the force on it from an electric field. There's a force on this that's equal to Q times E vector, the force that would be on it if there were no B field, plus the force that's on it from the B field, which doesn't care about the fact that there's also an E field on it. So it's just Q times E vector plus Q times V vector cross B vector. Okay? So it doesn't change. And so this gets us, there's a homework problem, and I don't want to do it completely because it is a homework problem, and so there's no point in me, if I show you too soon, you won't learn enough from it, but I want you to sort of physically see what's going on. So a little bit of a start on this. So in this problem, you're basically trying to understand this, make sure you sort of strengthening your understanding of this. So we're told that there is a particle that has a velocity that's 12.0 times 10 to the third j hat. So your book and other books jump back and forth between x hat, y hat, z hat, and I hat, j hat, k hat. So x is I, y is j, z is k. So it's just different notation. So we're told that this thing has a velocity vector of this. That many meters per second. We are also told, so if you're picturing, right, so this thing has a velocity, right? So if this is, let's say I hat, j hat, and then k hat must be coming out of the page. So it's useful to picture this thing. So this has a component of j hat and k hat. So it's but no I hat component. So it's moving, and its k is a little larger than its j. So it's moving this way. Right, it's a little more than 45 degrees because k hat comes out of the page, j hat goes that way. So it's going, so its velocity is this way, but a little more toward the upwards because that's bigger than that. And we're also told that its acceleration is equal to 2.00 times 10 to the 12th meters per second squared I hat. All right, so it's accelerating in the I hat direction. So at the instant we took the snapshot, is headed this way. That's its tangent to its motion. But it's accelerating in the in the I hat direction. So it's turning this way, right? But at this, I don't know, maybe it was coming around like that. But this instant, it's aiming this way, no I hat component, but it's accelerating in the I hat direction, right? So it could be something moving in a circle at this spot in time. It's heading that way, but it's accelerating this way because its velocity vector is gradually changing from this to a vector that points that way, which is an inward shift. Okay, so then B vector, we're told, is 400 microtesla, 10 to the minus 6 Tesla, in the I hat direction. And the question is, find E, find the electric field. And you think, well, Jesus, I don't know what the hell that is. Sorry, we also must be told, we're told this is an electron. Okay, well, so the basic idea of this problem, I don't want to do it all out for you because it is a homework. so therefore you know the mass of this object. So if you know the mass of the object and you know its acceleration, you know the force on it. So the force on it is going to be this times that. So the force on it is something I hat. So you can write down, so F is Q E vector plus Q V vector cross B vector. This, you know, that's mass of the electron times the acceleration vector. This is known. And this is known. And so E vector is going to be F vector minus QV cross B divided by Q. Will give you the electric field vector. Okay? All right, we should probably just stop there. Yeah, okay. So any questions first before we go? Okay, and I apologize for not getting back to our Name That Tune segment. That will return along with the version which has no benefit for people of different ages. I feel bad that we haven't gotten back to it because, right, so far we have Jordan, JP, Abby, and Brady are tied at, well, Alex, actually, I'm sorry, Alex has 2 points, but we have to return to it because right now I feel like we played one hand of poker and they got to get up and leave after one hand, and that can't be. So we will return to it. I just talked too much and ran out of time today. So have a good day, and I'll see you on Thursday or in office hours. Bye, all.
Have a good one.
You too.
Thank you.